keeping the other term constant, which is this one. Did you follow me this? Yeah, you follow that, right? So this is like a f times g prime. This is f times g. F is here, g is here. Yeah, you don't have, they have this name, right? So this is not so intuitive, but they thought about a lot and this come about like this. So and then we are going to finally use this one to be minus s, right? And then I'm going to even make it as t squared as st. Multiply both sides. So and then what am I getting here? Minus. So if you do the derivative of not g but g over t over temperature, keeping pressure constant, you will get minus t squared h. So that's an equation that you will get. So I wanted to have a look at this too. Differences. The original one is Gibbs free energy derivative with respect to temperature change. This one is a little bit more complex, but that's the one. Which is more useful? And it's up to you. And in terms of phase diagram, this is more useful. But in terms of actually quantifying something that is measurable, enthalpy is something that I can measure. Right? Entropy is a hard one to measure. So that's why more practical equation. And this guy's name is Gibbs-Helmholtz equation. This equation comes in very handy. And in the textbook, it doesn't show that clearly. But if you're looking at, if I write the other form, if I write it in this way, if I write d round 1 over t over round t. Do you know what this is? Just a derivative of 1 over x. Right? That will be minus t squared, right? You see that here? So this equation, I don't know whether it became more ugly or not. To me, it became more simplified by going this way. So what I can rewrite 1 over t, t over t, keeping pressure constant. So that's the equation. So this is actually the version that I like. Some of you might like this one better. This is the same form, but keeping this, instead of temperature change, 1 over temperature change. Instead of g change, g over t change. And that will be related to simply the h. That's a Gibbs-Helmholtz equation. Okay. So why is this so useful? Why am I actually, I'm very excited that I got to talk about this, because if you look at that, if I change this delta G, changing the Gibbs free energy, it will be delta H. We are getting something, right? So certain process, enthalpy is changing. If you know about the Gibbs free energy change over temperature, they are related, right? Then I want to jump ahead. This is jump two chapters ahead. I don't know. You probably have seen this one. I think that you probably, when you talk about equilibrium constant, reaction quotients, and stuff like that, have you remember seeing this? You take it for granted, right? I'm gonna get to that. I think probably I'm gonna use a similar one. But look at that, right? This G at different, and then this is the temperature, right? So what this equation is all about, I am going to divide this by T. And this is gone now. So what's important is what defines an equilibrium. Oh no, sorry. I was jumping ahead so much. So in equilibrium, under equilibrium conditions, this is 0, right? This is under equilibrium. Delta G is 0. That's equilibrium. Right? So it's actually, I have to, if I want to write a K, then it gotta be 0. Right? So I'm going to put this one down this way, this way. This one is not discussed in this chapter, but I think we can push the idea ahead. So I'm going to rewrite this one to once more, saying that now I'm shifting my focus onto this. So delta G over T is minus R natural log equilibrium constant. We are getting something extremely useful now. So look at that. This, based on the Gibbs-Helmholtz equation, this term is actually much easier thermodynamically meaningful term, because this term is not G over T, right? G over T, or somebody actually, I don't like this, so let me just say RT. So actually put an energy unit down here, they can do that too, okay? But anyway, this G over T is a thermodynamically more meaningful to define the equilibrium. And equilibrium constant is not proportional to K, but natural log of K. Right? And then this is essentially, I'm going to put because I'm not going to solve any equation. That defines a natural log of equilibrium constant, and that is actually not defined by temperature, but 1 over temperature. So think about this way. So when we change the temperature, this is I think one of the core concepts. When we change the temperature to change the equilibrium conditions, you are not, if you change the temperature, is not what you should think. You should think about 1 over temperature. That's the one. If I double the 1 over temperature, this will double, right? They're proportional to each other. The proportional quantity is not temperature difference, T1 minus T final. That's not thermodynamically meaningful. What's meaningful is your final temperature minus 1 over initial temperature. So if you do that experiment, sometimes, you can just put an x-axis of temperature, y-axis an equilibrium constant, you can do that. But if you think about it, maybe I can plot my data based on 1 over temperature axis, and then to represent the equilibrium constant, and I can get to my answer very well. So I think I don't know, in the high school chemistry textbook, you probably remember 1 over temperature. This is ln K, and then you got this equation, and that slope is minus R over delta H. And that's the one it actually can be stretched from what you actually start with from today. dG is ddP minus SdP. I mean, you guys can write this one from the scratch. You can go all the way in a single shot, right? But you can develop that kind of concept. Okay? Maybe I'm the only one who's excited about this one. But it's a Gibbs-Helmholtz free energy. This form, or even the form that I like, this form, 1 over temperature derivative with respect to the 1 over G over T divided by 1 over temperature. That derivative term has a nice consequence. Okay. Where is my remote control?